carbon, and we're going to just do this in the simplest way possible. We'll put an oxygen there, and we'll make another one and move it over here. Boop, there we go. Now, these here on the left side are called our what? Reactants, and then on the right side it's going to be our products, to make it really simple. So we're just modeling an equation using some little spheres. H2O, how many H's do we need for H2O? Okay, we need 2 H's, so should we take them from over here? There we go. There's 1 H. See if I can move this one a little faster. There we go. And I'll take one of those. All right. Amazing, I know. The things you can do with computers these days. Wow. All right. Now I added some extra things in here, so if I messed up on these, shouldn't have done that, huh? All right, CO2, I'm going to take this one, C. There's my O. Uh-oh, I ran out of O's. Let's add some more. So I'm going to add another mole of oxygen, O2. Whoop. There we go. And I'll add another, I don't think I need to see. There we go. So we add another O. Oh, there we go. All right. This C, I don't want that there anymore. Pardon me, I shouldn't have added it. Oh, what do I have left over on the left side? Oh, water. There we go. And we move it over. Now, that's a chemical reaction. That's the simplest we could possibly get. Remember, in this chemical reaction, we had the correct amount of ratios. We had 1 of these to 2 of those to make 1 of these and 2 of those. Right? Basic stoichiometry. So in this reaction, the next thing to know is, well, how much energy was changed in this reaction? And how could we know this? So what you had at the beginning we had CH4 and H2O. In the CH4 and H2O, in order for them to become CO2 and H2O, going from left to right, the first thing that had to happen is the bonds needed to break. Okay? One way of modeling this is, let's assume that all the bonds broke, completely broke up into all the pieces. Okay? If all the bonds broke, that means we would have the following things at some transition state. We would have oxygens, we'd have our carbon, we'd have our other oxygens, okay? All of these floating around at some state that we're going to call our transition state. And we've got 4 of these suckers. There we go. That'll make it easier. There we go. So the bonds first have to break. All of them have to be separate. That's one way of modeling. Simplest explanation is they all break up. They're all hanging out. Okay? So this is called a transition state. Now, this transition state, we don't know necessarily how long it lasts, if it lasts, even if it happens. But Hess's law says it doesn't matter how you get from the beginning to the end. It just matters the difference, right? So, after you break all these bonds, now to make CO2 and water, what has to happen? New bonds have to form. So you have to make new bonds or form new bonds. Okay? Make or form bonds. So it's pretty simple. You break bonds and then you make or form bonds. Now, to understand the energy change in this is one of the craziest things about chemistry. So let me go grab something crazy. All right, crazy stuff is happening. All right. This right here is known as a magnet or a coach symbol. Yeah. I don't know. It's some brand. I don't know. All right. Oh, I do have to show you guys the Hello Kitty poster I made. If you like Hello Kitty. If you don't look at it. All right. This here are 2 magnets. Some of you might already know a lot about magnets. Okay, the North and the South Pole attract one another, and they have a certain force of attraction. These magnets, however, are not normal magnets. These magnets represent atoms. And these two atoms are connected together, so they have a bond. They have a what? Bond. Now, they have a bond together. In order to separate them, all you have to do is do what? Pull. Add energy. Yeah, a lot of energy. That's right. And now, to put them back together. Listen. Listen. Oh, somebody hear noises? I heard noises. When you break a bond, you have to add energy to break the bond, to pull them apart. You're overcoming their electrostatic attraction. You pull them apart. Now, if they get close enough together, it's kind of hard to do this unless I get really lucky. If they get close enough together, they will attract on their own. I technically do not have to add any energy for them to stick together. These are magnets, not atoms, but atoms work on a similar process. The electrostatic attraction is called the Coulombic force, causes them to attract. The positive electrons are in this. The positive protons are here, negative electrons are around it. Positive protons are here, negative electrons are around it. These electrons attract this positive, these electrons attract this positive. These two are attracted to each other. You have to add energy in order to break the bond. But when bonds are made, that's when energy is released. In this case, you heard sound. In a flamethrower, you see light. The light you see has nothing to do with the wood that's being burned. You take a piece of wood, you light it on fire. The wood turns to char. You would think, well, you break bonds, energy is released. But it's not happening. What's happening is the bonds are being broken. You're adding energy to break the bonds. You have to start the fire, sometimes with alcohol if you're Mr. Christopher, right? Because you can't do it on your own. No. You have to add energy. You have to add enough energy for those bonds to initially be broken. Once those bonds are broken, the carbon dioxide and the water, when the bonds are formed by these two gases, these are both invisible gases you can't see. When the bonds are made here, they release so much energy that some of that energy goes back to the fuel and breaks its bonds again. That's why a fire will continue to burn. The charred wood is just this stuff, or the charred wood or the Cheetos. It's just this stuff, okay, breaking those bonds, and it's the new bonds that are forming. So energy addition, when you break bonds, you add energy. When you make bonds, you remove energy. So that means this diagram is showing an energy change. This is an energy diagram. As you go up here, let's see if I can draw this. As you go up here, this is energy. Right here you have the reactants. The reactants have a certain amount of energy. You have to add energy in order to get up to the transition state. You have to add energy. Then when you go from the transition state all the way down to the products, it releases energy. The energy that is released, the negative energy that's released, means that this reaction will be exothermic. The next question to ask is, well, how exothermic will it be? What if I change my fuel from methane to Cheeto to octane to dynamite? How would it change it? Well, it's all dependent on the number of bonds that are formed. So, this relationship says the enthalpy of a reaction is equal to the sum of the energy of the bonds that are, first of all, that are breaking, okay, minus the energy of the bonds that are formed. Now, this is one way of looking at it with breaking and making bonds. What Hess saw was, well, wait a minute. If we can find out how much energy is needed to form anything, we can determine breaking is just the opposite of that. So what Hess said was, well, the transition state, I'm going to make it simple. transition state, instead of being O by itself, I'm going to say it's going to be O2, because that's an element. All right? We don't find O by itself like this, or H by itself. That's not really how it's found in nature. So let's assume that it's not found that way, and it doesn't matter if it is or if it isn't, because Hess's law says it's the beginning to end is what we need. So what Hess was able to see was, let's say we had a reaction like this. Sulfur and oxygen combining to form SO2. The good thing about this is, experimentally, some of these experiments had been done before. Okay, just like you guys did today, you added chemical to water, and you measured a value of a value of T, delta T. Could you measure the heat change? Yeah, easily. You just do the mass of the water times the specific heat capacity of the water times the change in temperature. You could get the delta H for these reactions. So these reactions are given to you. Somebody else measured them, so you don't have to measure those. But you want to know this reaction here. So to do this, what Hess saw was, well, it has to happen in a series of steps. So what you can do is you can calculate the heat of reaction, the enthalpy of reaction using other thermochemical reactions, having reactants and or products in common. So all you have to do is manipulate the given thermochemical reactions to build the desired reaction and add delta H's together. So all you have to do is flip the reaction around or manipulate it so it adds up to the given reaction in the problem. So let's see how this works. First thing you can do is you can reverse the given reactions to mask the desired reactants and products. So we want to have an S and an O. Okay, we want an S on the left side. Which one has an S on the left side? First reaction or second reaction? Second one, so that looks pretty good. Okay, O2. Well, that one has an O2 and that one has an O2, so it doesn't help us much. SO2 on the right side. Which reaction has an SO2 on the right? Neither of them. However, there's an SO2 on the left of the first one. So what do we want to do with the first one? Reverse the first one, keep the second one the same, and we can see if just adding those together gives us what we want. So we got 2 SO2 gas plus O2. If we reverse it, what happens to the sign? Reverses. There we go. Does this remind you of a little bit of redox cells? Redox equations? Yeah, you do the same thing. You got potentials. You can do the same thing. So it's a very similar skill set. Okay, reverse the reaction. That reverses the enthalpy. Okay. The 2SO3. Okay, going to 2SO2 plus O2, that's our new equation. That's what it looks like. So the bottom one is just the new equation for the first given equation. So I reversed it. This is the new equation here, just so you know. So I rewrote that equation. Now, if we add them up, we might get our reaction we want, our S plus O2 making SO2. So to make sure we get that, we want to multiply or divide the reaction by factors to match the coefficients. So in this one, it says we've got 2SO3 making 2SO2. So what do we have to divide the first one by? 2 to get this coefficient to be a 1 here, there. So we divide the first one by 2. That gives us this reaction. The heat is divided by 2. The second reaction, what do we have to divide that one by? 2 as well. So we divide that one by 2. Okay, the negative 790 turns into negative 395. Are we good to go so far? Okay, anyone miss anything I did there? I know with the animation sometimes it's hard to see, well, what are you dividing by? Okay. So we divided both equations by 2 because we wanted to get the exact equation that's written up on the top. Now, once you have that, you add the reactions together. So that's the third step. You add the reactions together. So these are our new reactions, the ones in black on the bottom. We then add them together. SO3 plus S plus 3 halves O2 makes SO2 plus 1 half O2 plus SO3. Okay, and from our knowledge, if it's on the left and right, what can we do? Cancel it out. So we cancel out our SO3 gas. And we can cancel out only 1 half of the oxygens. You see that? So we started with 3 halves and 1 half. 1.5 on the left, a half on the right, cancels out a half of them, 1/2 a mole, and that gives us the SO2 making SO2. That's the equation we wanted. Once we have the equation we want, the last step to do is just to add up the delta H's, to add up the enthalpies. So negative 395 plus 98 is the last step. So you add the delta H's up. Negative 395 plus 98 is negative 297 kilojoules. That's the heat for the reaction. You just determined that this reaction produces 297 kilojoules per mole of fuel used. From this, you could determine how much energy is released. This is an exothermic reaction because the delta H is negative. Yeah?
Just wondering, back when you were divided backwards, why did you divide by 2 for the second one and not by 3? You could have, like, because there's 1 O2, so you could have done 2/3 plus O2.
The main reason what I saw, which, again, there might be slightly ways of varying it, is the S. I had a 2S here. I wanted to get that S equal to this, and I didn't know if I had any other S's to cancel out. See how there's no more S's? So if I didn't divide this by 2, I would never have that S, and I could never have the actual equation. So if you divided it by 3, you would have 2/3 S, and there would be 2/3 S here, and it would not be the same equation. So that's why you match up the S's. When you have, oftentimes, oxygen's on both sides, just so you, or when you see something that's on both sides, that's often the thing you don't want to make sure is equal because it'll cancel out and give you the final answer. So I was just looking at this reactant, the sulfur, and the product, the SO2. So my concern was the S and the SO2. I would rearrange the equations until I got those the way I wanted to, and then the rest should work itself out. So let's try a delta H problem using Hess's law for this reaction. So just like the previous one was a step-by-step reaction, okay, here we're going from H2O solid to H2O gas. So you have a solid piece of ice, you want it to turn into gaseous water. What does it have to do first? You got ice, you want it to turn into gaseous water vapor? Got to turn into a liquid. And then once it turns into a liquid, it has the ability to turn into a what? A gas. Now in this case, it's going straight from solid to gas, so we have to determine the delta H for this reaction. All right, let's look at delta H. You might have already done this. Shouldn't take too long once you set it up. So we have to start with solid first, right? So which equation has solid, first or second? First. What do we have to do with the first one? To get the solid on the left side? Reverse it. So we reverse the sign. Second one has liquid and then gas on the right. We want the gas on the right, so it's good to go. So we add these two together. Those two cancel out. H2O solid to H2O gas, that's the heat of reaction. I'm sorry, the enthalpy of a reaction, 46.72 kilojoules. That's it, you're done. Same idea. This is a physical change, but same idea. Step by step by step by step. Okay? So let's try this one here. Okay, 2-minute quiz. Let's see how far we can get in 2 minutes. On your mark, get set, go. Oh, sorry. Timer. There we go. You got 2 minutes from now. I'll give you 1 extra second. Ready, set, go. All right, ladies and gentlemen, this type of problem may take a little longer than 2 minutes for you right now. That's okay. But let's see where we're at and see what we've done. See if you started out correctly. Even if you're not done, the first step is to do what? What would you do? What would you do? You would divide the last equation by 2, okay? All right, you also can flip it around. So he's looking for the C2H2. Very good. That's how you would get the C2H2. How would you get the 2 C's in the beginning? First equation by what? By 2. Very good. And then how do you get the 2 H's? The H2, I'm sorry. Second one, you leave it as B. All right? So how would this work here? We double this, double that, double that. That causes that to be doubled. We leave this one the same. Then we divide this by 2. Okay? So divide that by 2, 2.5, 2, 1, and then that's half of it. Right? We reverse it. So that reverses the sign. The whole entire thing reverses, which I'm not going to write out, but I could if I wanted to. And then all we have to do is add these up together here. So I'm not great at doing decimal math in my head, but I will just write this out. 2 times 393.5 today. So this equals 787 negative. That's kilojoules for the first equation. The second one is negative 285. And the last one is 2598.8 divided by 2. This is positive 1299.4 kilojoules, and we add them up. Negative 285.8 plus negative 787. As long as you keep track of all your negatives and positives, that looks like a value of 226.6 kilojoules for the reaction as written. On a problem like this, usually the concept part of it, usually okay, I just flip this, divided by 2 or whatever, is usually not too bad. Where's the mistake usually made? Oh, I forgot to flip a sign. Or, oh, I didn't divide by 2, even though I divided the whole rest of the thing by 2. Or I just punched them into my calculator wrong. Okay, it really stinks if you do all the work, you understand all the concepts, and you're not careful enough to punch it in the calculator. It happens to the best of us, but this here, 226.6, is this a positive or negative enthalpy? Positive. Does that mean it's exothermic or endothermic? Endothermic. So this is an endothermic reaction. Does that make sense? You're taking an element, and you're making a compound. So you need to add energy to do that. You're forming a new compound. If you break up that compound, it releases what? Energy. If you took this C2H2 and you burned it, it would release carbon and hydrogen. So this reaction going forward absorbs energy. Going in reverse, it releases energy. Yes?
Didn't we just say that forming bonds releases energy?
This is correct. This is for the whole entire change, though. So you are breaking some bonds, and you're forming some new ones. In this case, the breaking of the bonds needs more energy than the forming of the new bonds. In this case, it's positive. So let me show you what it would look like. Picture right here. Here's an energy diagram. This one here started here. The reactant started here. The products at the end had more energy. So the products here had to absorb energy from the environment. That's why this is an endothermic reaction. So in this case, our reactants are these things. Our product is this. Did we still have to break bonds? Absolutely. Did we still make some bonds? Absolutely. But which of those two events had more energy transfer? The breaking of the bonds in this case. So we needed to add more energy to break the initial bonds than to form the C2H2. And so it's not easy to predict this just by looking at an equation. That's why we would need this delta H data. This is what it tells us. So this process here is exothermic, C plus O2. This one is exothermic as well. This one here is incredibly exothermic. But when we reverse it, it makes it incredibly endothermic. So yes, the basic breaking of bonds requires energy. The making of bonds releases energy, but you have to add them up to get the total. And that's the change in enthalpy. Now, what we did earlier today is we added chemicals to solution. All right? This is called the enthalpy of solution. Not that fancy. It's still enthalpy. It's still solutions. So you guys mixed a chemical in a solution of water. The enthalpy tells us the heat generated or absorbed when a certain amount of solute dissolves in a certain amount of solvent. So here are the enthalpies of some ionic compounds. If you look at the ones we tested today, calcium chloride gives out 82.8 kilojoules per mole. It has the largest negative number. What does that mean? Does that mean it's exothermic or endothermic? Exothermic. Negative delta H. Which one of these would make the coldest solution per mole? Ammonium nitrate. We used ammonium chloride, which it was colder than the sodium chloride, right? Now, we don't know if we used the same molar amount, right? We didn't know for sure. But relatively speaking, this agrees with our experimental evidence. So we could measure the heat of the solution. All we have to do is do our Q equation. Q equals mass times change in temperature times the specific heat capacity. And when we do this equation, our Q, where did they get these numbers from? The Q of the water, okay, the heat given off or absorbed comes from the chemical, the ionic compound. That goes into the water, and the water either absorbs or releases that energy. And that's dependent on the mass of the water, change in temperature of the water, and specific heat capacity of the water. Now, there is a reason why I write this equation like this here. Doesn't matter how you write it, it's multiplication, right? So the cool thing is N stands for what? Mass. T stands for what? And C stands for what? Okay? The other good thing is my first name is Matt. My second name is Thomas. My third name is Christopher. I was born to use this equation. And if you put that together, you could call me Q, but then it would be a Star Trek show. All right, so James Bond, yes, I could be Q. All right, so cool thing is enthalpy of solution. The cool thing about this is you could have this happening. Liquid solvent, it could spread out. Solute crystal could spread out. When you have a solution here, when they come together, this makes our change in enthalpy. So when they mix, the combination of the solute and the solvent can create energy or absorb energy, right? You can form it, break, push the exo or endothermic. Either is possible. It depends on the what? Depends on the solute and the what? Solvent, and how they attract or repel one another, right? Some things mix, some things don't mix. Some things give off heat when they mix. Some things absorb heat when they mix due to their chemical properties. And ultimately, it goes back to their bonds, which we will learn about later, speaking of Q. So, delta H1 and delta H2 are usually endothermic in order to break the intermolecular forces and bonds. So in order to separate out the liquid solvent, to move it away from each other, you have to break the bonds, right? Endothermic, endothermic, endothermic. But when it comes back together, it's going to be what? Exothermic. So wait a minute. You've got these two competing factors. Whichever one is bigger tells you whether it's going to be exothermic or endothermic. Does it require more energy to spread it out, or more energy is released when it comes together? Which one is winning? So it's a competition. That's why you can have it either being exo or endothermic. The heat of a solution is equal to the sum of all of these enthalpies. So Hess's law works again. The total is equal to the sum of all the enthalpies, step by step by step. Each step, this one's going to break apart. Then this one's going to break apart. Then this one's going to come together. Then that one's going to come together. Could you have like a billion steps if you wanted to? Yeah, that'd be a waste of time, but yes, you could. You'd be like, yeah, I'm going to do it for every single molecule. That'd be fun. There's only 6.022 times 10 to the 23rd of them. No, you can't do that. You know that. Well, you could, but you'd spend more than your lifetime trying to do it for 1 mole. Now, the solution process for sodium chloride. Sodium chloride, did it get warmer or colder? Solution got colder, so it's an endothermic reaction. So here, first thing is these are solid state. The first step is you have to separate them out. Now, for NaCl, to separate them out, this is the energy needed to get them from a solid to a gas. That's a ton of energy. We didn't turn them into a gas, we just dissolved them in water. But then what they have to do is they have to go into water. So you've got 788 minus 784, which equals 4 kilojoules per mole. So the heat of the solution, 4 kilojoules per mole, here, it's positive. Positive. If it's positive, this process is what? Endo or exothermic? Positive, it's what? Positive, it's what? It is endothermic. Exo is releasing, losing the heat, getting rid of it, passing it on to somebody else. If I got $10 in my pocket and I give away $10, I got negative. I'm in my negative. I'm in my bad zone, okay? But I'm giving it away. If it's positive, that means I'm getting that. Okay? It's endothermic, absorbing the energy. What that means is the water is going to be colder. Did the temperature go down of our water with sodium chloride? Yes. The one group who chose to do that. Who did, eh? You guys did? Whoever did the salt. That's the hardest one for people to understand. Wait, that's endothermic. This is endothermic. This process here is what? Exothermic. But the endo beats the exo by 4 kilojoules. Okay? So step 1 plus step 2 equals our total, which is positive endothermic. Yes, sir?
If it's endothermic, it's absorbing heat, right?
Yep, from the environment, which includes the water and the thermometer. Yeah. I know, it sounds kind of weird. People go, wait, it's absorbing energy. Yes. It's absorbing from the water. That's why the water's temperature goes down. All right? Now, dilution. The cool thing is when you dilute a solution, there are heat changes as well. So tomorrow we're going to be working with some solutions, and we're going to notice these changes. For example, if I took sulfuric acid and I added water to it, okay, it gives off a ton of heat. Ton of heat. It must be done in an ice water bath. Okay? Sodium hydroxide, when you dissolve sodium hydroxide, you have to do that in the ice water bath as well, because it gives off a ton of heat. You know the calcium chloride? This stuff is put in swimming pools. My best friend, not a chemist. My best friend, I repeat, not a chemist. He was working at a swimming pool that I worked at as well, although he was somewhere else that day, different place. We worked at the same camp, and he took calcium chloride. And his boss told him to put some calcium chloride in the pool and told him how much. So he measured the right amount. He put it in his bucket, measured the right amount, put it in his bucket. Okay, you had to add a little water to it before you poured it in. He added water to it. It was a bucket like this. As he was walking to add it into the pool, went to go to put it in the pool, went to pick it up, and the bottom of the bucket melted out. The plastic completely melted because of the exothermic reaction of calcium chloride and water. He was very fortunate that it didn't hurt him too badly and burn him because the water was at very high temperature, but it melted the plastic. He learned that day, as well as I did from his mistake, that you do calcium chloride in a metal bucket only. His boss told him that, he just forgot that. And it broke right through because the heat of just adding the solid to the liquid gives off so much heat it can go through. If you did this, sulfuric acid, you added water to it and it got too hot and you didn't put it in an ice bath, your wonderful, fabulous, absolutely wonderful 1,000 milliliter beakers that we broke a few of already, remember? Okay? Pop, the bottom pops off and you're like, oh, it's just sulfuric acid. Oh, I don't want that. So you don't want to be, you want to be real careful when you're making solutions that you see, okay, is it exothermic or not? It would be really nice if you didn't experience the sulfuric acid on your feet. You want to know what's going to happen before you do it. Now, this is why you want to do as you order, you want to add acid to water. The water has a high specific heat capacity. So if you add the acid to the water will absorb some of that heat, right? If you add the water to the acid will give off so much heat that the water that's on top of the acid will boil and explode. And that's why you add acid to water and not the other way around. Okay? Now, the cool thing about Hess's law is it depends on the state of matter you're in. So we had solid, we had liquid, and gas, water. The energy for all those changes is different. This is also true for the arrangement of atoms. And this leads us into what are called allotropes. Okay? Allotropes have different structures, but they have the same pure element. One particular allotrope here is oxygen. Oxygen is a colorless gas. We use it to breathe in. It's essential for combustion. This here is not O2, but O3, known as ozone. Okay? Ozone is a blue gas. Just in case you don't remember, if you see colored gases, what should you do? Run. Ozone is an extremely toxic gas. But ozone, up in the upper atmosphere, is necessary to protect our Earth from ultraviolet radiation. That's not why the sky is blue, though. No, I wish it was that easy. It's actually easier than that. It has nothing to do with the ozone for why the sky is blue. It has to do with all the rest of the molecules. Now, phosphorus is another one, another element that has allotropes. For these different allotropes, it's pretty cool, these different materials. if you increase the pressure of white phosphorus, okay, it changes colors into a black phosphorus allotrope. If you increase the temperature of white phosphorus, okay, over 280 degrees Celsius, it turns into red phosphorus. If you heat it for 1 to 2 weeks at 550 degrees Celsius, you get violet phosphorus. And this is also used, white phosphorus by itself was used in grenades in Vietnam. Some of the most dangerous grenades, because the phosphorus would heat up so much that when it reacted with the skin, it would continue to boil. And it would destroy the person who got hit with white phosphorus grenade. It's kind of like a grenade with hot, fiery phosphorus liquid shooting out of it. Yes? Good question. Yeah. So the theory that you said, the hypothesis you said about the sky being blue has nothing to do with the ocean, because as you said, if you're over land, you don't see that reflection. That's not why it's blue. So you're absolutely right. That was a false statement. That is not why the sky is blue. Why is the sky blue? How many other people would like that answer right now? Yeah. That's a good question. All right, that's a good question. So. All right, so it is totally relevant because it influences the colors you see here. Okay? Why is this white, this red, and this violet? This is white because you can see it's a much smaller allotrope. This is black, much larger in structure. It absorbs more light. This one here is red. It absorbs all light except red, which reflects back out. That's why it looks red. So light is composed of 3 primary colors. The 3 primary colors of light are red. See if I can do this with an eraser. I got my green here, maybe. There we go. So the color of everything you see is determined by the light that is absorbed, reflected, or emitted. So the first thing we have to do is, where does that light come from in the first place? Sun. Now the sun. Here's Danny right down here. There we go. Big smiley face. There's your coat, your bag. There you go. That's you. Coach bag. Yeah, you don't need coach bag. Plastic bag. All right. Sorry, I don't want you to bankrupt your family or friends. All right. So the sun is up here. Now the sunlight is an interesting color. If you look directly at the sun in the middle of the day, which you're not supposed to do, what color would you say it was? Okay. It's mainly, it's almost white, almost perfectly white. The reason it's white is it's composed of the 3 primary components of light. Oh, that's a bad picture. I'll draw it better.
So which idiot was it who suggested that we draw suns yellow in our class?
That's not an idiot. Let me show you why that idiot was actually right. Why did the person say we draw suns yellow in art class? And what color is the sun when the sun sets? All right, so let's take our sun. In the middle of the day, it's white. The reason it's white is because it's composed of red light, green light, and blue light, which is shining through our atmosphere. At noon, our atmosphere has a particular distance. The light is shining through all the molecules in our atmosphere between us and the sun. It's a lot of molecules. However, all of the light, or almost all the light, gets through. That's why it appears white to Danny. But it's not quite white. Some of you even say it's yellow. Kind of, but I don't know how yellow. What happens is, if you deflect just a few of these blue photons, you get red and green. Now, the really crazy thing about red and green, which is totally counterintuitive, is if you take red light and you put green light with it, like a stoplight, the middle one is yellow. It actually makes yellow light. Now, I can't show you that right now with evidence, so you can choose to believe me or not. And that's okay. I'm fine with either or, but you get a yellow color. As the sun changes its position, as it goes across the sky in the daytime, the angle of it going through the atmosphere changes. Now, the atmosphere is the same distance, but when the angle changes, what happens to the amount of molecules that the light goes through? It increases. You can even see this much better, and it's hard to show this, but much better when the sun is like totally at the when the sun is setting. When the sun is setting, some really cool things happen. The first thing is the blue light has the smallest wavelength, and some of this is getting through to Danny, but a lot of it is deflecting or refracting off of the molecules. All the molecules, the nitrogen, the oxygen, the ozone, everything that's in there. The smoke when it's in the sky causes a really red color. Lots of diffraction. But the green and the red are also going through. So all of these colors of light are going through towards your eyeballs. The question is, well, why is the sunset red then? Why is it red? Now, some of the green, as you get more and more atmosphere, some of the green gets refracted. And the really cool thing is, the sunset gets this red and violet color and all these other cool colors. And then, right when the sun goes down at the very last minute, you get a very special occurrence. And this is when the sun is perfectly setting, the red light just misses your eyeball. It goes right over your head, and the only thing you see left, because most of the blue is diffracted, is the green flash. So this is what is happening with the light. This is why the sun changes colors throughout the day. Okay, it gets yellow, sometimes it gets like an orange, a red. It's not going to be perfectly red ever. Okay, but it'll be a variation on the red color. The clouds have these purple colors. Why is that? Because the blue is deflecting and hitting the clouds along with the red that's shining into the clouds. You get those purple clouds. This is why you see the sun to be the color it is, and this is also why the sky, the sun up here appears light yellow. Light yellow is due to these two colors. So if these colors are coming through, what color is not? The blue. That means the rest of the sky is going to appear blue. Okay? Because the light has to go somewhere. It can't just disappear.
Is that light or water?
Water being blue does have to do with the light traveling through the water. But water, if you take a sample of water, it looks clear. So how does the water turn blue if it looks clear initially? Is it just reflecting the sky, or is water actually blue when you look through, like when you go to SeaWorld? Or did they just paint the concrete? Yeah, it's whale water, right? Yeah. Or did the whales poo blue in there? That's why. I mean, what is going on? Now, those are great questions. Semi-serious? All right. About safety.
So you said we should like run whenever we see a colored gas.
Uh-huh.
Shouldn't we run whenever we look up then? It's not a colored gas. But it's like air and
It's the light. It's the light that you're seeing. So, okay, if I look at you and I see a yellow shirt, should I run? No, the light that's reflecting off of you is yellow. It's not the gas. All right. Now, I have to tell you, one thing that's even cooler than the color of light is carbon. Carbon is the coolest atom. Carbon can be all sorts of fun things. This here is a general shape of diamond. It's got a three-dimensional tetrahedral shape. However, if you take it and you flatten it out, the carbon atoms can have a distance of 335 picometers between them. This makes it graphite. Diamond, extremely hard material. Graphite, very, very smooth material. Okay? Graphite is the most stable allotropic form of carbon. Energetically, it's the most stable. However, it's not the only allotrope of carbon. In 1983, Buckminster Fullerenes a buckyball. Now, this was a while ago, so it's not quite the newest one. This buckyball had a very symmetrical shape. The carbons fit together in a perfect structure. And some people even imagine if you could put something inside of it, you could transport it to something else. This is what was used by graphene, which has different structures depending on zigzag, chiral, or armchair configuration. You get different properties of graphene. Nanotubes are the next thing that were designed. These nanotubes, depending on their chiral, armchair, or zigzag, they would flatten this out and they round it together to make what looks like a pillbox out of a molecule. All of these have different properties, and they try to put medicine inside of these that can be slowly released. This is one medical application of allotropes. This one looks like straight, this one looks kind of curved, and this one curved the other way. Okay? These structures here are called nanostructures. They're used in medical devices, or trying to use them more often in medical devices. They're called devices because they're not drugs, but they are made of chemicals. They are low friction bearing assembly with 2 carbon allotropes. So they're going to try to make machines using these small nanostructures. A machine that could operate at the nanoscopic level. So this here looks kind of like a wheel, and it can go around this axle here, just like a little car would. You could be having little nanostructures driving around in your body, or some other science fiction like that. So this is a nanomechanical gear assembly for making a car inside your body. No. Or maybe I should say yes, I don't know yet. So tomorrow we're going to be doing the next lab probably. So make sure you bring the next lab number